Hi, this is Huda Zenham from Physics 2212, and this is the fifth lab of the semester. To introduce, the purpose of this lab is to observe how long it takes for a magnet to fall through an aluminum tube, and then connect the information found with Faraday's law and the computational model we make in glowscript. So the concepts that we need to know are Faraday's law, as shown above, and Biot-Savart's law, shown below. The procedure is to create an aluminum tube and then take the dimensional measurements of the tube and the magnet and record the magnet falling through on a recording device such as a phone, and then trim the video from the time it starts dropping to when it stops to get the exact duration, and then repeat the recording 5 times so that we can find an average time. So here are my observed measurements. I did the trials 5 times, and they're all around 1 second, but the average time ended up being 1.196 seconds. And then I have the length, width, and inner radius of the tube, and I have the mu from lab 3 as 3.95, and our mass of the magnet. So for our glowscript code, we have to initialize some factors. We have physical constants such as mu over 4 pi, resistivity, and the gravitational constant. And then we initialize a graph, or later on we will see the velocity versus time graph, and then create the tube of the aluminum foil by setting up the geometry of it. We have, again, as shown before, length, width, inner radius, and then the overall radius, which is the width plus the inner radius. And then we have properties of the magnet, such as the mass and the mu of the magnet, as shown before again. And then you create a model of the magnet, and we have initial conditions. The velocity starts out at 0 and time is 0 because we are dropping it. And when you drop something, the velocity is 0 at first. And then we have to create a function to calculate the magnetic field of the bar magnet. And we did this again in lab 3. And then we create a function to calculate the magnetic flux. And in both these, we use the formulas necessary. Next, we have the gravitational force, which is in the negative y direction, and that is mass times the gravitational constant. And then we have the current on the ring, shown here, ring.current. And then we have the magnetic fields at each ring that we have to calculate at the bottom. And then we have the net force, which is the magnetic force and the gravitational force combined. Then we use the velocity and position update formulas to update the velocity and positions for the velocity versus time graph. And then we plot the graph and print the time that it was in the tube by subtracting the exit time and the enter time. So these are the results that we get when we run the code. We can see there's a simulation of the magnet falling through the tube. This is our model. And then we have the graph using the mu that we have from lab 3. Here we can see that it also shows us the time in the tube as 1.935. So very similar as to the actual one that I got before in the real example in real life. So what if resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So the induced current would be large due to Ohm's law, and the time it takes for the magnet to fall through the tube would be larger as well. What if the holes or slots were cut into the tube? How would this affect the ring currents in your model? There would be less rings in the computational model, and the time to fall through, induced current, and magnetic force would all be reduced. So we can see that there's a certain relationship that when we cut slots in the tube, this is decreasing all of these components. Thank you and have a great day.